Okay, we're going to be looking at the fundamental theorem again, and we're going to be looking at the fundamental theorem with relationship to accumulation functions. And just as a reminder of an accumulation function, let's think about, let's say that there's an accumulation function a of x, which equals the integral from some constant. Let's just say, let's call that constant c up to x of some function. And I'm going to actually give a function. So let's say the function is t squared plus 1 dt. And if I wanted to find out, so here's my accumulation function. If I wanted to get an actual equation without a definite integral, what I would do is take the definite integral. So by finding the antiderivative, so it's going to be 1/3 t cubed, and again the 3 and the 3 are there as they always are when we're taking the antiderivatives, plus t. So that's the antiderivative of 1, and we're evaluating it from c to x. And when we do that, we will get 1/3 x cubed plus x minus 1/3 our constant cubed plus our constant. And this is my accumulation function. So for any value of x, this tells me how much I've accumulated from c. All right, well, what about what would be the derivative function? Well, this is a very interesting question. The derivative function, or the derivative of an accumulation function. The derivative of an accumulation function it's going to get back to the same thing. Why? Well, when I take the derivative of 1/3 x cubed, the 3 drops down, and we get x to the 3 minus 1, which is 2, plus the derivative of 1, sorry, the derivative of x, which is 1, minus the derivative of this constant. And remember, even though it's c, it's still just a constant number, and the derivative of a constant is 0. So what we do, or what will always be the case here, if my accumulation function is some constant to a value x, the derivative of my accumulation function will be the same as the original inside, only instead of t's, now it's in terms of x. Neat. Very neat. So this is said kind of succinctly right here. It's if f is a continuous function on some interval a to b, and an accumulation function is defined such that a of x equals some constant to x of f of t dt, then the derivative of a of x, or a prime of x, is just my little function, little f of t, but instead of having a t in there, it's now in terms of x because we plugged x in. So let's just look at a real quick example of that. So, given a of x is the accumulation from 2 to x of, let's say, e to the t times sine t dt. Here's a challenging function, but if I said, what is the derivative of my accumulation function? Well, using this identity that we just developed, we can say that the derivative function is e to the, instead of x, instead of t, we have e to the x sine of x. And this will tell me my rate of change of the derivative, the rate of change of my accumulation for any value of x. All right, well, let's do another example, finding the derivative of an accumulation function. We can do it the slow way and then the quick way. So the slow way would be to say, all right, let's take the antiderivative, and we get that f of x equals 1/3 t cubed from 1 to x, and that equals 1/3 x cubed minus 1/3, plugging in x and 1, and therefore the derivative, now we just take the derivative of that, and what we get is, dropping the 3 down, we get x squared, and the derivative of 1/3 is just 0. Well, the quicker way, that's the slow way. The quick way is for us to recognize, well, given that it is an accumulation function, the derivative is just my inside function, t squared, but instead of a t, we replace it with x. All right, so let's look at a slightly more challenging problem. We've got a rational function here that we're integrating from, so we've got g of x, an accumulation function from 1 to x of 1 over t squared plus 1, and it says determine an equation for the tangent line to the graph of g at the point where x equals 1. Well, so what we need to find 1 comma g of 1, and that'll be our point. And we also need to find g prime of 1, because that'll tell us the slope of our tangent line. Well, let's first find g of 1. G of 1 equals the integral from 1 to 1, because we're saying x is 1, so we're replacing x with 1 of 1 over t squared plus 1 dt. And we don't know how to integrate this yet, but since our limits of integration are 1 to 1, we know that anytime you integrate something with the same limits of integration, we get 0 back. And why is that the case? Because there's no width to our width for our area. And then what about the slope? How do we find the slope? Well, we know, given what we've been talking about this lesson about accumulation functions and their derivative, that g prime of x equals 1 over x squared plus 1, just replacing the t's with x's. And therefore, we can find g prime of 1 by just putting 1 in for x, and we get 1 over 1 plus 1, or 1/2. And that's the slope of my tangent line. And I know that my tangent line has the point 1 comma 0. So therefore, we can easily find the equation for this tangent line. The equation for the tangent line will be y equals m, my slope, which is 1/2, x minus 1 from right there, plus my y value, 0. And there's my equation. Notice, even though this wasn't, an integration, there was an integration problem here, we didn't actually have to do any integrating. I mean, I guess sort of we had to understand that when you integrate from 1 to 1, the result is going to be 0, but we didn't have to find any antiderivatives. Okay, now it says find the numbers of x for which the function defined on this interval by the equation, this accumulation function, when does it take its minimum value? Okay, well, let us think about this. We know that our derivative, f prime of x, the derivative function, because it's an accumulation function, is just going to be sine of x. And when it takes a minimum value, the derivative, knowing what we know about minimum values or maximum values, that occurs when the derivative equals 0. So if we set our derivative equal to 0, this will occur. We know that sine of x, and just here's a quick little graph of sine x. We know that sine of x will equal 0 when x equals 0. And that's in our given interval. So we could create a derivative chart, x and f prime of x. And here we have x less than 0, x 0, and x greater than 0. And referring to the chart that we just drew up here, we know that at 0, our derivative is 0. To the left of that point, we are negative. And to the right of that point, we are in the positive values. So because my derivative goes negative, 0, positive, that implies it's minimum. So find the number x for which the function takes its minimum value. Voila, we did it right there. And we did it by finding the derivative of our accumulation function, setting our derivative equal to 0, like we did here, making a derivative chart just to make sure that it was in fact a minimum and not a maximum. Okay, so this next idea is just a little bit trickier. And what I want to do, there's a slightly complicated set of equations up here. But what I'd like to do is think about an accumulation function, a very simple accumulation function that goes from 0. Instead of going to x, let's go to x squared. So from 0 to x squared. So now, instead of accumulating up until x, we're accumulating to some function f of x. And the function that's accumulating, let's say, is 3t squared plus cosine t dt. So if we were to integrate this, to simplify this, to get it out of the integral sign, this would equal, well, the integral of 3t squared is t cubed, and the integral of the antiderivative of cosine t is sine t. And we know that because the derivative of sine would get me cosine. So if the derivative of sine gets me cosine, the antiderivative of cosine is sine. And we're evaluating this from 0 to x squared. And that's my accumulation function. Okay, so what's going to happen here? Well, when I plug in my value, instead of just turning into x as it has been, my accumulation function is going to be x squared cubed plus sine of x squared. So when I take the derivative, function, a prime of x, it's not just going to be this inner function where I replace the t's with x's. It won't be, because now I have an inner function that I have to be concerned with, and it's basically going to we have to consider the chain rule. So my derivative, when I'm putting a function in, is a little bit more complicated. So let's just think about what that derivative would be. Well, it's going to be 3 times x squared squared. That's taking the derivative of something cubed. The derivative of something cubed is 3 times that something squared. And then times the derivative of the inside, times 2x. Plus, well, the derivative of sine of something is cosine of something, times the derivative of that something, 2x. So notice it's almost like we just replaced t with x squared. So we have 3 times something squared and cosine of something, 3 times something squared and cosine of something. The difference, and it's a huge difference, but the difference is that multiplied at the end of each of these terms is the derivative. It's the derivative of my limit function. Okay, so how could we summarize this in a nicer way? Well, what we can do is we can say that let's start a new page, and let's not use that pen. If we're integrating from some constant to x, not a function, but just x, and here's my accumulation function. So we recognized that given this scenario, the derivative function was just f of x. Well, if our accumulation function is dealing with a function instead, let's call it g of x, then the derivative, just like we saw before, the derivative is going to be f of g of x, and then times that additional component, which is the derivative of my limit. And you could memorize this rule, or you can really sort of think about it and understand it. And let's just do another example without this rule, without using this rule, and then see how we could use the rule. So for example, let's say I want to integrate from 2 to, let's say, cosine x, 2t dt. Well, if I wanted to find the derivative of my accumulation function without using that rule we just developed, we could say, well, this equals t squared, so take the definite integral, evaluated from 2 to cosine x. So now we're just finding a of x. And this equals cosine of x squared plus 2 squared. And now that I've found a of x just in terms of a function, no integral signs, we know that a prime of x, just take the derivative. Well, we're going to need to use the chain rule. So it's cosine squared. So something squared becomes 2 times that something, and then times the derivative of the inside. So times negative sine of x. And then plus 0, because the derivative of this is 0. We don't need to put plus 0, but I'm just writing that so that it's, just as a reminder. Okay, that's doing it by hand. That's doing it the long way. Or the other way, if you kind of wrap your head around it and understand this rule, what we can do to find a prime of x is just plug our function in for t, and then we need to multiply it by the derivative of that limit, so times negative sine of x. And as should be expected, whichever method you choose, you're going to get the same one back. And it should be pretty clear that the second method, if you learn that shortcut, will save you tons of time. But it's important not just to learn the method, but to understand that method. Okay. says do the long way or and the chain rule. I'm going to change this to or. So what I'd like you to do is just take a second to try to find the derivative of y with respect to x. So y is an accumulation function, so find the derivative. I would urge you to do it both the long way and the chain rule, and then I will do both. So pause the video, take a stab at doing this, and then unpause it once you have a solution. Okay, doing it the long way. The integral from 0 to x squared sine of t dt equals negative cosine of t, because that's the antiderivative of sine, evaluated from 0 to x squared, which equals negative cosine of x squared minus a minus, so plus cosine of 0, and cosine of 0 we know is just 1. Well, if I wanted to take the derivative, now just kind of unwork what I just did. So taking the derivative of negative cosine of something becomes negative sine of that something times the derivative of the something, which is 2x. The negative and the negatives become positives. And the derivative of cosine of 0, well, that's a constant, so that's just 0. Okay, so that's doing it the slow way, the long way. Or what we can do is we can say, well, let's just plug x squared into t, so we get sine of x squared times the derivative of that x squared, so times 2x. And that's the shortcut way for finding the derivative of an accumulation function that has a function as one of its limits. And they are the same, which makes us very happy. And that's it. So just to kind of go back to the key slide that I think you want to make sure that you're comfortable with, and that's right here. So the idea being this top equation is when our limit, when we're just integrating with x is one of our limits, and then this bottom formula is if we have g of x as one of our limits, so a function is one of our limits, and when we have that, we replace t with the g of x, and we make sure to multiply everything by the derivative of g prime of x. Okie dokie, that's accumulation functions or derivatives of accumulation functions.